And so I think let's start the panel by asking all three speakers to basically either raise questions for others or have some parts that you wanted to emphasize that you didn't have time to do, that you find it relevant in context of the whole panel and the whole meeting. So please go ahead. I think if there is nothing, just to get started, I would really like to beat on this one a little bit. We just finished the spring course on principles of modeling for changing power systems at MIT. It's going to be edX course, it was advertised. It really digs into this very question, how do you model the physical system? And under some assumptions, you can make it the graph in which you understand input output. Under some assumptions in this distributed interactive environment, I think we need to rethink the modeling big way. So I don't know what other Pascal or Tamer. I think this is exactly the literature that you were referring to, that I'm pointing out. Yan is not any longer with us, but that is really a fundamental issue that would be important to understand for the changing industry. Pascal, I think you want to say something, right?
No, I think I agree that it's the specification of the model is a very interesting point.
Yeah. And so this is not to say that it's not valid.
So the thing is, we've been talking about multi-agent systems.
Yes.
Who are the agents in the case of a power network, power system? You have all the users, you have the utilities, you have other sorts of adversaries intruding into the system. How do you, how would you know when you are confronting with a system as to who the agents are? I think that's one of the fundamental problems, and what their inputs into the system, either as disturbance or either positive or negative inputs are. And that also ties in with Jan Williams's work in the 1990s.
Yes. And so I think, Pascal, I would like you to describe a little bit the market players and stakeholders for people who are not familiar, but there are many, many agents, right? And they interact over different time scales and different layers. You have aggregators, you have individual, users, generators that get aggregated into portfolio. They talk to system operator. Pascal, if you want to take it from there and talk a little bit, but I think this link is extremely important. This is the change of paradigm that we have in power systems. It's not, Tamer, you were asking, how do you know? I always ask, who are you, right? Because there is no more one entity, it's all interactive, right?
No, so I completely agree. I think that there is a paradigm shift that will happen in the next couple of years for sure. I don't think how you can actually start controlling these very large grids where you have a kind of the boundaries between the subsystems and the systems are disappearing, where you will have a lot more incentive to actually act locally. And so how do you do that? I think is a fundamental open issue. I'm very interested in that topic, actually. It's not easy, but I think this is also an area where you have a lot of connections between control, between optimization, between machine learning. And I think this is very unique, because you have a real large-scale application driving this with physics. And also, I think the critical issue of reliability and managing risk. So I think for me, this is I agree with you. It's a fundamental open issue where the three communities have to work really closely together.
And Tamer, thank you to connect, Tamer, with what you were talking about, the agency. I think what is happening, it's really intriguing from the game theoretic point of view. People don't do competitive games only anymore. They do cooperative, depending on which level you are. So when you have the aggregator serving the neighborhood, that's a cooperative unit, but it may compete with the other neighborhood. So we sort of have a mix of distributed clusters of different stakeholders and market participants or grid users, but depending on which level you are, they're
Yeah.
either cooperative or competitive.
I mean, you have to bring in aggregation. The question is, I mean, when you are talking about networks and nodes and networks, so you have neighborhoods, and how can you capture the behaviors of those around you? You cannot consider them as single individuals, because as single individuals, an individual's impact may not be that substantial, but collectively it could be substantial. So the aggregation is a big issue. I think the power system, in power systems, definitely a lot of time scale separation work has been done, Maria, as you know, and then some aggregation work has been done in the past, but that has been at the physical layer for
Yes.
systems. And now you have decision makers, individuals making an impact on the system. How can that be aggregated? I mean, one thing I have to mention is recently in game theory, by recent, I mean, for the last 10 years or so, the mean field game theory has become an important sort of a tool and analysis framework it has provided individuals. And we are now able to solve problems which we were not able to with even a small number of players. And when we take it to the limit to a high population, so therefore each player or each or one or two players see an ensemble of decision makers, and then you can any individual irrationality there is actually absorbed in and does not impact the overall performance that's coming from there. So I haven't seen much work in on the side of mean field games applied to power systems, but this is something I would think is a future research topic.
Going again, Anna, to graph theory people and Jose Moura, and I think that Shomi Akkar did something for his PhD thesis and now as a faculty on these mean field game theory applications to power. However, the results that I've seen, there are two issues. One is that it's sort of all these results only hold in the limit, right?
Yes, yeah. Well, you can also show you prove results in the limit, high population, but then you say, let's have a large population, but not infinite. How much do you lose? What sort of epsilon optimality do you get? And do you, if you are looking at robustness, do you suffer from robustness? If you have enough margin, you may not, when you go from the infinite limit to a finite, but still it has to be a large number. And you can have order relationships there.
Yeah, that would be really, it's very relevant for this changing industry because, you know, I've been in this for a while and, you know, the reason that all the industry works, they have everything aggregate. The system level load is very smooth. Everything is fine. But if you go and look into one by one, things are very stochastic and they look pretty ugly. You cannot say anything about that. So there is this question on epsilon. What is the minimum size that makes sense to do the aggregation so that, you know, something holds? Either you increase efficiency, you participate in the market, making money. There are all sorts of million of questions, but it's sort of, this is my personal comment and I should not making too many personal comments. But the thing is that there is very little work in power area which tackles questions this way. So I think it's very open for systems thinking and for games and so forth. Like one thing that I wrote, and I think it's both for Pascal and for Tamer, where do we start reconciling robustness and efficiency? Because markets are all about efficiency. People are just going to make money. And how do we have tools which are going to look at some of these trade-offs?
Well, you have seen what has happened in Texas. I mean, that's a security. If you go for efficiency and so on, the whole system has collapsed. So you have to have some resilience built into the system. and that's provided with an active sort of a robustness building into the system. In other words, not only protecting the system against sort of the adversarial attacks, but also teaching the system how to recover from such attacks, if it is within some reasonable thresholds. So I would say there is a need for both, and I'm someone who says, I mean, people used to say in the past, you are doing minimax work and or robustness and viewing everything as adversary. That's too pessimistic. So what I say is, this framework allows you to be as pessimist as you want to be, or as optimist as you want to be, by bringing together different sort of concepts or notions. And robustness is one issue, and the efficiency is yet another issue, and making decisions, quick decisions, maybe is another issue that has to be taken into account.
Great. So Anna, I think for you, but also for Tamer, because he put tons of those equations that way. If you look, I see Pete Sauer in the audience. If you look at his book, the models that we have for power systems is high order for dynamics, high order differential algebraic equations. That is the starting point, because you have very complex dynamical models in the nodes, Anna, as you described, and it's subject to these constraints on power and so forth. How do you guys have any idea? In the course that I was teaching this spring, people ask that question. How do you go from that state-of-art modeling to now applying any control to all these and so forth?
The question is,
because models, things that we know how to do in control, they are just basically standard state-space form, right? You have ordinary differential equations. What is the state of art to go from DAs to ODEs?
so the question is for me?
That doesn't matter, yeah, please.
Okay, yeah, no, well, I had a very simple dynamical model, which was the swing equations that inspired
So that's
some of
already
the
standard state-space.
But yes, and I recognize that's very simple. But ultimately, if we take the kind of the data science point of view, a model that is perhaps not based ultimately in every aspect on the physics, but is good enough to describe the data for the inference problem at hand, is oftentimes preferable, because you may not know perfectly the parameters of the system. So you want to learn something relatively simple from measurements that captures the gist or the essence of your data. And so I'm taking truly sort of this data scientific approach that you could see this completely as a black box model. And I am also just though acknowledging that there are certain modeling facts that are based in the physics. So you can't be completely ignorant. But in data science, generally, for generalization purposes, it's always good to try to find the simplest model that makes sense.
Okay, so we have a comment from, that was Johan, sorry. In reinforcement learning, if you are taking a deep reinforcement learning, can
yeah, so sorry, this is me answering one of the questions.
Could you please pose that question? I can't find it and answer it, yeah.
So the question is from Venkateswara. So he asked how would this be essentially helpful for dividing the network and enforcing control strategies on different parts of the network. So the slant of the talk I gave was mostly concerned about data science, detecting things or making inference, not control. But because the structure of the data shows that the impact of certain things, of the signal itself, is the impact of certain parts of the system is relatively weak. This can give somehow the idea that by clustering the network, you can somewhat divide and conquer the problem of controlling the system and looking at the impact. Obviously, you don't want to cause cascading failures, but in most regimes, if your control action is not particularly brutal, it should essentially have localized effects. Now, for the that is true for the inference problem and also for the control problem. What GSP more in the control framework, just also to connect it with Tamer, could be useful for is to, if you take an approach where you can want to find, for instance, a policy through a neural network, right? So in that case, you will want the policy also to perform this feature extraction that is common in analyzing data, right? So it is true that, you know, convolutional neural networks have been conceived for analyzing images because they are a good feature extraction tool. But similarly, if you have a policy, most likely this policy in a deep neural network will benefit from extracting what are the important features of the state that you have observed so far. So once again, the architecture for these neural networks is very important and is related with the structure of the data. You cannot apply sort of a generic architecture and be as successful as if you use an architecture that is good at doing the feature structure for you. And so that would be just a connection.
Thank you very much, Pascal. I want to move to your differential privacy.
Yeah, okay. So I just wanted to say that what Anna said is also connected to what Tamer has said before about aggregation, about
yes,
yeah, and I think there is a strong connection.
So I wanted to ask the question. It's in context of a differential privacy, but I think it's really in context of everything, robustness and signal processing. I think in power systems in particular, with a lot of power electronics, we are reaching the stage that the ratio between noise and signal, in particular when you worry about cybersecurity, is not so good. So when you, many times, Pascal, you said in your presentation that you have the optimal benchmark, right? And then you perturb it a little bit, either for feasibility or optimality, depending on which method you are using. At least the experience that I've had, and I've worked with a lot of physical systems, this question sort of reminds me big way of the struggle that power systems people have with state estimation, because data is really very polluted, not clean. So, you know, we can compute optimal power flow, but we really don't know what it is, right? Yeah. And then you perturb it by a little bit. So this becomes a moving target. So how do we, what do you compare with when you mention you're doing optimal power flow, you maybe are doing OPF to map the state estimation, measure data the best way to power flow, and then you take it from there. Can you elaborate a little bit on that whole problem?
So I think in this particular case, I think you make a good point. I mean, this is always the same, right? So you are approximating a physical system, right? And then afterwards you have the state estimation telling you exactly what happened. Now, right. the point is that even if there is noise in what you are predicting and noise in what you are observing, that noise doesn't guarantee per se that you are going to preserve the privacy of the load or the generation. And because, I mean, yeah, I mean, it's a noise which is completely different from what is happening there, right? And so I think the key point is that you want these guarantees, whatever the noise, whatever the difference between the theoretical, optimal power flow and the real state estimation. And so I don't think this is too, the algorithm are still going to be completely valid, right? So because I think what you're doing is adding even more noise, but by definition, the noise that we have is already private enough. And this is this beauty of the post-processing immunity in a sense, right? So whether you put the noise before or after, we are fine, right? In a sense, because I think what you're protecting is significant change, right? So you're not protecting you are not protecting, tiny changes. That's this notion of alpha indistinguishability. And I think the beauty also of differential privacy is that you're actually controlling that. You're really controlling what you want to hide and where you want to hide. And you also can balance that with the price that you are paying. So I think that's one of the things that I don't know if it came across nicely, but you fully control the level of privacy that you want, and therefore the level of noise, and then the suboptimality that you induce.
And this is the agent does that or system operator?
So I think you can do that you can do that in different ways, right? So so there is this. So what I talked about today was this notion of global differential privacy in a sense. So this is the most you get the most guarantees. But in practice, there are a lot of applications that have this local notion, and then you can actually do some of these things yourself. And I think it will make a lot of sense when you have this distributed system, more decentralized system. So people will add the noise independently. Yeah, I think that's a good notion. And then you have this notion of local differential privacy, which is actually much easier from a computational standpoint, but provide fewer guarantees, because now you are in the context of a particular data set.
So the example of gas electricity, you brought up a really interesting thing about bit validity. Where is the boundary between gaming and something just being expensive?
So the reason I brought that up there is because, in a sense, I think, and this is one of the, so the bit, I think there is a lot of potential. And this is one of the things that I wanted to mention before. There is a lot of potential in changing the market such that you make the system more robust, more resilient. And there has been a lot of resistance to that, right? So the market is what it is. It's very difficult to change. And when you were answering the question of robustness, I think part of it is the fact that the market is there. People don't want to change it. And therefore it's tough to actually add a new notion of robustness or take that into account. So I think some of the ISO, for instance, are more interested in looking outside the market on how you build this robustness. And so I think your question is very good. I think the bit language should be much, much better. I completely agree with that. So I think this is where we can make a lot of progress. Yeah, and the other thing that I think is happening, and I know that this is an issue, is that some people don't want to reveal the data, right? So, and I think in the kind of distributed system that we will build, there will be, and this is again a very interesting topic, there will be this market of data. People will actually create market, and you can buy the data or you can bid for the data as well. And I think there will be something which is interesting, is this trade-off between the quality of the data and then the quality of your solution at the end. So that's also a very interesting point. So in addition to everything that you said, I think there is this additional level of market in addition to the game, to the games. There is a market on top of it.
I think
that market is a little bit more sophisticated would be interesting.
I've seen work by Munzer Dalek here at MIT and a few other people. They're already talking about markets for data. Yeah, it's fascinating, actually. Yeah. I just, before I lose this signal to noise ratio, because it's an important one, when it depends, most of the stuff that we're talking about, markets here and scheduling, that is a sort of quasi-stationary, static time scale, right? But if you go to these things that are popping everywhere, microgrids, small things where you have just, solar PVs connected to EVs and stuff like that, completely different technologies that you have closer to the end users. And most of this stuff is now controlled by power electronic switching, right? So you have inverter controls on solar, and depending on how good the inverter controller is, things are going to stay stable or not. Some people are working on that to that level of detail, very fast dynamics. How do you, the power electronic switching, how do you make sure that that stays stable? Now, if we think about that, we can think about that as a deterministic thing, models are given and everything. But then I think there is an entire program that DOE has, or ARPA-E, I forgot, where they talk about, can you make these microgrids cyber secure, right? And so there you say there is some noise, tampering noise, what I don't think anybody is looking at, depending on the nature of that noise relative to the fast signal, you can do different things or you can't, right? Because it is such a fine time scale. It's not even mechanical, it's not even swing equation, it's even faster than that, electromagnetic. You can have inverters on wind power plants and inverters on solar fighting if they're not tuned right. And that is at a, much shorter than second time scale. And then you superpose some noise for tampering. If you put the noise, which is very slow, you get one type of problem. If you now put very fast white noise, you get completely different problem. It would be really interesting to know from the control people, this is, I guess it goes to time scale separation, Tamer, again. You can have slow and fast noise relative to the signal. Can you guys comment a little bit on state of the art on that?
Well, the thing is, I mean, we have used time scale separation in this algorithm that in what's called adversarial reinforcement learning, where you have a virtual adversary that you bring in. And the virtual adversary responds to what you have done on a faster time scale. So you have to have an accurate sort of an response from that. So you have to, even if you cannot obtain the exact response of the adversary to your input, if you have an approximate sort of response, which you obtain by creating a virtual adversary and running it on a faster time scale, then we have been able to prove convergence. But this is a separation at the algorithm level. It's not separation in the sense of interacting with the system. Now, it is possible also to formulate interactions with the system based on need, and that will lead to, again, a time scale separation of some sort. Some of the agents may interact with the system on a much slower time scale as need arises, whereas the others could be operating on a much faster time scale. So I think this is a very natural sort of a framework for power systems and utilities and so on. Those who will be operating on or making decisions on a slower time scale will just look at, these are generally would be threshold based. If a certain threshold exceeds, then you interact with the system and submit an input. And if things are going normal, then these slow time scale agents do not provide any input or do not interact with the system. So that's my, so you could have it at the algorithmic level, you could have it at the decision-making level, as well as, of course, we have seen a lot of work in the past with singular perturbations applied to power systems.
Thank you. I think there is a related question here. Says at system level, fast sample data like PMU measurements on one side and fast acting devices, inverter control, smart inverters for power electronics that we were talking about on the other hand. It's really noise at high frequency, they sampling theory. And other aspect is supraharmonics, or so what do they call that, supraharmonic? The subtransients, we call them in power systems. Supraharmonics or subtransient concept from smart, creating future issues where you can have strong overlap with noise at the system and high frequency. So, Mr. Reddy, this is really exactly what I was bringing up. So, I think this is where signal processing is important, to somehow understand where is the difference between the signal and noise?
Yeah, quite frankly, actually, it wouldn't be such a difficult task for signal processing, because the fact that you have harmonics is not only that you have a sparse signal in the frequency domain, which is one of the raging areas, has been for many years in signal processing, and how you sample these kind of signals in a reduced fashion. But also, you know that the harmonics fall in certain particular frequencies, so that even simplifies the problem. So rather than having phasor measurement units, one should have information about these harmonics. Each of them, since they are centered at different frequency, will come with an admittance matrix, which is recentered in that particular frequency. And what's important is to understand the interaction, what happens at this other frequency, and what is the potential impact on controls and other mechanisms that safeguard the network. So why is this not done in industry? I guess is because people are very concerned with selling the current PMUs. I am hoping that the new generation of technology would capture these harmonics response of the grid, because it's not that hard. It wouldn't add a tremendous amount of data. And as I try to outline in my talk, these data are highly compressible. So it's just a matter of, you know, right now we are still in the phase where everybody's enjoying using PMU data, but in the future, you're right, there is going to be definitely a large impact from these power electronics that creates all these harmonics and other phenomena.
I will talk with co-organizers and back to C3 folks, but it almost sounds that we should, as a community, start creating some problems, you know, for power area problem is being proposed, because the question, why is nobody using it in the industry? An example, and there are some people from power area here on the call, so they can maybe comment on that. ERCOT has this, what they call control-induced system stability problem, in which you have controller on the wind power plant fighting the controller on series capacitor, which is again power electronically controlled on the weak line, and they cannot measure it. So this is, I mean, that time scale is creating fundamental challenges to, I think somebody was talking here about rethinking Shannon sampling theorems. And
right. I mean, I was trying to say that has been done. It's called finite rate of innovation sampling. It's known as, if you have a sparse supporting frequency, you can actually sample at a rate which is comparable to the bandwidth that is occupied, not to the zero components of the spectrum. So these are very applicable to this context. In fact, it's simpler because you know where they're centered.
Okay, so let's go back to an example that I know of. You have a little inverter control solver, right? And you want to connect and disconnect to utility, depending on the price. And okay, if you look at the simulations of that thing, and you have several sub-processes, one from kilohertz switching of the power controller. The other one comes from whatever filter you are putting there to clean harmonics. Yeah. The third process, this is just heaven for timescale separation, Tamer. And then the last process is when you connect it to the utility. Utility has high inertia, which moves slowly. So you have a combination of things that you don't know. What is harmonics? What is it caused by? And how to model it. This is where we actually stand. This is the state of, can't just say go and apply this theorem. We don't have these models formalized as a community.
No, but even if we don't have the model, I mean, the harmonics will be always a multiple of the 60 hertz, right? Because the original signal goes through complicated non-linearities.
Okay, so let's go back now to Shannon theorem.
Yeah.
The models that we use in power systems, they are dynamic phasors based. That means that the voltage magnitude and the phase angle are changing slower than carrier frequency, which is 60 hertz, right?
Now,
okay. Now superpose on this 10 kilohertz. Even that time varying phasor is no longer valid.
So the 10 kilohertz is not an harmonics. It's some process.
No, 10 kilohertz, you're doing your controller that way, very fast. With the power electronic switching sees the error and opens and closes the
So you
switches
have a
and
low frequency component that is not created by some nonlinearity operating on the AC signal. It's some,
created by very fast switching of the inverter control.
but is this centered at 60 hertz or is this operating on the phasor or not? I don't know.
Very good question, and I think we are avoiding all of those. This is, I think, why the control community now has to do some work in what are the relevant models when you have power electronic switching. Even the people like George Verghese, Chris DeMarco, we introduced these time-varying phasors 20 years ago. They're beautiful, but they only hold if the carrier frequency is much faster than the phenomena that you superpose on the modulation. And the minute that, I think we have a problem with power electronic switching, that because this PWM switching by inverters is moving very fast. You close and open very fast to get rid of low harmonics. That's how it works. So you don't need big filters. This comes from power electronics. And then you mix them up and you no longer know what's what. I've been involved a little bit in some of the projects on that on the Lincoln Lab side, but I can tell you that it is very interesting, both opportunity and challenge for the community. So rather than me talking too much, maybe there are some other questions. Or do you guys have any questions, panelists, for people who gave talks, or any thoughts how to connect different ideas? If you, during the talks, if there was some thoughts you want to share now. Let's see, what did I have?
Maybe you can ask Pete Sauer what sort of wisdom he will provide.
Yeah,
Pete, are you there?
yeah, he's here.
Yes,
But I don't know how to unmute him. Larry, can you unmute him, or Jay? I don't have command over unmuting.
Who would you like to unmute?
Pete
Oh.
Sauer.
Ask to unmute. Okay, so what is your wisdom in all of this?
I think he's still muted.
Yeah.
Yeah, I don't know.
Okay. Okay, he can go ahead now. Pete, you can unmute.
I think he's still muted.
He can unmute himself.
Pete, can you unmute yourself now?
He may be distracted.
Pete, can you unmute yourself? Okay, so you leave that for University of Illinois discussion when you go back.
Okay, sure.
Okay. I had, Tamer, can you tell us a little bit more on your ideas on multi-agents? Where is that all going? What are
Well,
the
I think, the challenge in multi-agent, I mean, we haven't applied it to power systems. But the main challenge is that if each agent is using some machine learning algorithm, how are you going to treat normally with single agent reinforcement learning? You make some assumption about the environment, and generally that's a stationary environment. And you develop algorithms under that assumption, and you try to learn that environment, and this improves your performance. Now, if you have multiple agents, then each one is trying to do this, then from each agent's point of view, other agents become a time-varying non-stationary environment. And so that's where the challenge is. And you don't want to coordinate the actions of these other agents as well. And so we have, made some progress in that area, particularly with zero-sum games, Markov games, but but still for non-zero sum games, it's still work in progress. So that's the main challenge. What do you? I mean, there is an environment which is not under the control of the agents. That's one thing, but there is also, which could be stationary, but there is also an environment created by the actions of the agents themselves, and you don't even know what sort of algorithms other agents are using.
Yeah, and that really is a little bit related to this Williams modeling issue. But I think there are some preliminary results which show that it's not completely decentralized, but if the agents talk and exchange information about this shared variable,
Right. Yeah.
yeah, then things can be, you know, you can induce by self-adapting, you can induce feasibility. But the catch is unfortunately that it requires change of local control on the agents so that they actually, they say, we are going to make my shared variable that way, that they actually have the control inside to do it. And this is exactly the way, you know, this interactive control is going to, and you can do a lot of that. I think the only reason for coordination at the end of the day probably is because of the, you know, you have many, many players. How do you discover, how do you talk to everybody? Like when John Cisiklis was talking about complexity of doing decentralized control in period, because you have many players. But if you have a few players, you can show that by having a protocol in which there are two types of protocols. One is that, and this has been practiced in power systems now for ages, that each balancing authority cancels its own imbalance, and then the thing is balanced, right? That's how frequency is regulated in power systems. That's competitive. But I think what's more interesting and more efficient is that you have a protocol which says there should be some required information exchange, you know, which is going to bring these you know, different distributed, decentralized agents to work together. We are pushing, in my group, we are pushing some of those ideas, but I was just curious about.
Well, the thing, I mean, you mentioned, you said if we have just a few agents, then it might be doable. But on the other extreme, and that's what we are looking at, if you have a very large number of agents, then their actions actually could lead to a stationary environment. For me, so there is an advantage of having a large number of agents as opposed to a very small number of agents.
Right.
And sometimes you don't even know how many agents there are. So therefore, if you go to the high population, then you avoid knowing exactly how many agents there are, as long as it's a large population.
Going back to structure, I think, Anna, that you were trying to emphasize, there's a lot of structure in power systems models. You know, if you look at the models, my dynamics depends only on the dynamics of neighbors, you know. So there is a lot of to build on that structure when we do the multi-agent thing. There is a question from Panos Mutison. He said in the Dominion Energy region, there have been PMU measurements, this is for you, Anna, detecting some 8 Hertz, mode near photovoltaic, low frequency oscillations, basically 8 Hertz, and near photovoltaic rich areas, which adds more concerns further to those of the carrier signal frequencies. In other words, you're not getting the 60 Hertz only. There is this low frequency.
Yeah, so let me just wear now the sort of signal processing hat, right? Signals and systems. So if you don't have a narrowband signal, as you were saying, Maria, around 60 Hertz, or you don't have harmonics that are also concentrated around certain frequencies, then the way of looking at the signal is to take the Hilbert transport. Now, the problem is that type of signal is not easily compressible if you have a large support. And when I talk about sparse sampling, they would assume that this 8 kilohertz or 20 kilohertz signal that you didn't expect to land there because they are not harmonics of the 6 years, are also narrowband around those particular frequencies. So if you have this nature of the signal, you could still apply a reduced sampling rate which grows with the support, the total support of all these components, even if you don't know where they land. So this theory of finite rate of innovation sampling exactly handle these type of cases where you have these signals that have low degrees of freedom compared to the highest frequency that is representative of the signal, because they have all these narrowband components. Nonetheless, what matters is really the total support that they occupy in the frequency spectrum, not how large is the maximum frequency that you have to capture.
Okay, so Panos wants to follow. If we can just can you ask to unmute Panos? And I think it's on the same subject. Larry, can you unmute Panos?
Yes.
He raised his hand here.
Yep.
But
Hello,
that's
thanks for
Yeah,
giving the opportunity to elaborate. It was more of a comment actually, because I was saying it was an 8 hertz, not kilohertz
Yep.
mode.
Yeah, actually, it doesn't make any difference theoretically in terms of number of samples.
Yeah.
But then the problem is, if you're trying to estimate the frequency, the lower is the frequency, the more you have to wait, because basically it appears, many times it appears like a constant, right? So
I was also
so
mentioning,
Panos, did you want to finish?
yeah, I want to say that I was mentioning it also as an addition to your comment, Maria, about what happens with the carrier frequencies and how they will affect our analysis of stability, of modes, and so on. So until recently, we had the slow modes of rotating masses from generators, which were around the 3, 4, up to 13 hertz, at least in the 50 hertz system, because I used to study them when I was back in Europe. And now here in the Dominion region, where we hear about the 8 or 22 hertz, this is kind of vague. It is Luigi Svanfretti's work with Dominion, very recent work, and he's doing some analysis now. And this might be coming from low modes of low speed control, like for example, as I suspect to be the MPPT. So the MPPT, the maximum power, sorry for the initials, so maximum power point tracking has a circle of about a few milliseconds, but more than the electrical cycle. So this frequency might be matching, this mode of 8 hertz might be matching the MPPT behavior. So we seem to be breaking down the spectrum of frequencies in multiple chunks, and we'll have to address their effects in stability from with many different ways. And this adds up to what Maria was saying about especially the carrier frequencies and its effects. Thanks for your time.
Yeah, thank you, Panos. I think going back in time, some of us have been around for a while, almost 30 years ago, maybe, I don't know, 25 years ago. We did a project at MIT. Jeff Chapman did his PhD thesis with New York ISO, and it was motivated by 0.7 hertz oscillation between the small generator in New England and some generator in New York when you lose nuclear power plant. Okay, and this is the challenge. This is where we are getting, I see Vijay, probably, I think we are our mechanics here is not working very well, but Vijay was the one who did first studies on fundamentals of inter-area oscillations. These are the electromechanical inter-area oscillations. And Panos, I think we now have the one with maximum power produced by inverters, that is electromagnetic one. And when we tuned our controllers, going back to fundamentals, you tune your generator against the static equivalent. And then you put wind power plant, tune it another static equivalent for the worst case, whatever it is. You put them together and then you hope that it would work. This is what's happening on the power system. So we have really big job to do on, as we go over this scheduling for efficiency to integrate renewable resources, we really have to revisit the question if all these fast dynamics are going to stay stable and how are they going to be controlled. So I think there is another question and then we're almost out of time. Is there any issue in resolving conflicts among agents in distributed control algorithms. That's, yeah, exchange of information among agents in case conflict. Do we impose any penalty on agents in those cases? So, Tamer, Anna?
Well, I think all of the above. So it very much depends on the case at hand. And sometimes you don't want to share any information. And sometimes information that's shared could be strategically manipulated. And so that has to be taken into account. I mean, we all talked about data, receiving data that is maybe corrupted with noise. But what about if data is corrupted intentionally,
Yep.
strategically? And so if you have conflicting situations, then you have to take all of these into account. And so one has definitely, you cannot come up with a theory which will apply to all scenarios. It's very much scenario dependent.
Yeah, so I think we are out of time. Let's just close with one thought. I think what I learned here is that you can't do machine learning and these new data-enabled tools out of context of physics. And there are many, many time scales, many levels of granularity that we have to worry about. And so there is room for everything, right? But going from theoretical results to some tools that industry can use, I think that's a challenge in its own right. And probably we should work a little more proactively to connect with the industry also, to map whatever we are doing, all of us, in our papers, to what does it mean for some type of papers, problems that like Panos is bringing up, right? So thank you very much. This was really exciting.
And thank you, Maria, for doing such an excellent job in monitoring this.
Thank you. It's great to see everybody, guys. And take care. We'll reconnect maybe with some sessions or special sessions at conferences. So this is why this workshop, to get people to connect. And so there, as you know, there are opportunities in everything, in different communities to organize special sessions. So, and to try to zoom into some of these questions. I don't think all of them are sort of straightforward answers. Thank you.